Hello everybody, this is lecture 5 in signal and system. Today we will speak about the systems. What is a system and the properties of the system. In mathematics, system is some operations or some processes that you apply to an input signal. Then this is the operation that have been done in the inside the system. Then you will get an output. This output, a signal, is different from the input. That's what we call a system, the effect of the system. So the output have some different properties from the input. So this system for continuous time signal or discrete time signal, for x of n it gives y of n, or x of t gives y of t, have some properties like if it is affected by the delay, if I make a delay, if I give the to the system input after some time, what is the effect? If it is bounded of or it is unlimited, what is the effect? Linear or non-linear? So we will cover these properties today. First, the stability. I want to know what is what if the my system is stable or not. The stable means that bounded input gives bounded output. Pipo. Bounded input gives bounded output. So the system is stable. I give, for example, 5 volt. It gives always 5 volt. The mobile phone, for example, it's always working on a stable electricity, because if it is, for example, your charger takes the 22 volt from the electricity provider, and then gives the phone, for example, the phone need 5 or 7 volt only. If it gives for to the phone to 220, then the phone will damage. So this is a system but not stable. It gives, for example, one time 100. It doesn't give the accurate number or the expected value or the expected output that I need. So stability here, it is general the general property or the general description of the stability, means that a bounded input gives bounded output. The check, I want to check if my system is stable or not, if and only if bounded or limited in numbers. Bounded means less than a value, a number, finite positive number. For example, x of t, the value of x of t is less than, for example, 5, 4, 2. So it is for sure less than infinity. For all t, you take a summation, or we will see results, the output y of t results in unbounded output. Bounded output means that it is again less than my. So it, which is in, of course, less than infinity. Maybe my and mx is different, but it doesn't matter. The thing that is matter the most is both of them is limited, both of them is finite positive number, both of them is less than infinity. So let's say let's see an example. The moving average system. Moving average system is a system that's counting the average but in moving in time. So it takes the current 3 or 4 or a number of elements or instance of the signal, and divided by their number. For example, it takes 3 version of the input and divided by the number. This is what's called moving average system. So now he asked me to show that the moving average system is the which is described in this equation. is stable or not. Maybe it's stable. It is stable, but he is asking me to check why whether it's stable or not. Okay, first I write the equation, the very simple equation: x of n less than m of x less than infinity. So I will assume that x of n equal, see here, it's less than or equal m of x. So I will assume that x of n, I will write x of n equal m of x. Okay, and I will the superposition here to remove each x of n and put the m of x of n. Okay, now y of x, I write that my equation, then I will write the, I will remove this one to put m of x. What about x n minus 1? What is the difference between x n minus 1 and x of n? The difference is that's the same but shifted once, yes, to the right. This is again shifted to by 2 to the right. So it is the same value. It doesn't affect it here. It does it's affected in time, not affected in value from outside. So it is the same actually value. So m of x, m of x, m of x, all of them use summation 3 m of x over 3, so it gives me m of x. So I put, assume that x of n equal a finite value, and I find that y of n, the output, equal to m of x, a finite value. So this is a very simple and direct solution to find if my system is stable or not. So this system, I say that it the system is stable. You, after showing that, you will say that this system or the name of the system is stable, like this. Okay. Another example about the unstable system. Let's say here we consider this system y of n equal r to the power n x of n. Okay, show me that it is stable or not. Okay, first I will assume that x of n, again the same idea, the same way, x of n equal to m of x. Okay, less than or equal, so I will assume that's equal to m of x. Okay, so then I will apply that to the y of n, the absolute value of y of n. Yes, the absolute value of y of n is x of n here to the infinity. Yes, so when n goes to the infinity, so x of n, because here if you see for all t, so what if I sum all of them, or I get a very large number of n? So x of n here, it is a value, a good value, a small finite positive value. However, there is a small number from outside. What about this number? Let's say if r is 1, if r, this r is 1, for example, so 1 to the power anything, it is 1. So 1 multiplied by a finite number, then this system equal gives me a finite number. However, if r is higher than 1, for example 2 or 3 or 4, then it will diverge. Diverge means that it will increase, because n will increase. As n increase, this value will be very large, then it will go to the infinity if you take the limits. So the output here is not a finite number. It doesn't give me a finite number, so it's not sufficient to give me a finite or bounded or limited output. So I say that this system is unstable. This system is unstable because he said that r is larger than 1. If he specified that r equal 1, for example, then this system. What about if I remove r to the power 1 and I put cosine or sine? Cosine of n or sine of n or 2 by n, whatever. So what is the high limit that cosine go up and go down? Cosine is moving from -1 to 1, -1 to 1. Or I put a, for example, a value, a value a finite number of value multiplied by a finite number, it will give me a finite number, not infinity. Yes, whatever the value of n. So you should consider the function that outside x of n here. You should see that this, because this is the effect on that's affecting or gives the bounded or non-bounded or output. So you should see here cosine or sine, for example, tan, all of them gives bounded output, because whatever the value inside, it goes from 0 to 30, 60, 360. All of them goes from -1 to 1. So what uh, I multiply by an m of x, which is, for example, 10. I multiplied by 1, -1, 0 0.5, 0 0.0, 0 0.1, -0. It's actually giving me what? Actually giving me a finite number again. So this is another example that you may think about. I think there is some problems in the book. Uh, Now the second property of the system is the memory. Memory means this system have a memory. This system save a value inside it, or use a value that is depends on a different version of the input signal. Different version means even if it is in the past, I save a value from the past, or I expected a value from the future and I put it. Okay, what is the past and the future? The shifting in the time scale. We shift the signal in the time scale. Okay, or n. So only if the output depends on past or future or a version of or value of the input signal, then I have a memory in this system. This system have a memory or has a memory. So if only depends on the present value, for example, y of n equal x of n, only this is or a of n or r to the power n of x of n, then I have only, I look inside the brackets of the x of n, not the outside. Outside I don't care whatever the value outside, because each property I just check if this property happens or not. Okay, so here, if the only depends on the input value, only the present value, then it a memoryless. We say that this system is memoryless. Okay, so a moving average system, which is a very popular system, y of n equal to 1 over 3 x of n plus x of n minus 1 x of n minus 2. This is the present, this is the past because it's in the past, a version of the x, but shifted to the past by 1, shifted by to the past by 2. So both of them in the past. So as we said here, depends on the past or the future. So we have a past and the future, one of them. So we have a past here. So I will say it has a memory. Okay, it has a memory, or this system is a memory, or this system is a memoryless. Okay, so you should, this is the solution, just like this you specify where is the present, where is the past, why it is a memory or memoryless. This is just like checking up, checking out what is the this system about. Okay, or the property of the system. Y of n equal x to the power n. X to the power n, as I said before, we don't look to the outside, I just look to the inside the bracket. Inside the bracket I see only n, I don't see any other parts or sections of the system, so I only see a present, so there is no past or future. Then as we have here the condition for the memory property, then this system is memoryless. So all the examples or problems in this idea is going like this. You should check up. Okay, another example here. This system or this problem say that how far this memory of the moving average system describe it by the input output relation, how far in the past or how far in the how far memory have it have. So I have the here the present, I have here the past, I have here the past, but in the past or the future I save last one, then I save the previous one, and then I save the previous one. Then how far I got deeply on the past, that I save, for example, 2 here. I return back 2 values from our x in the past, and I save it in the memory, because the system actually is a device that you have in your hand. So I have a 2 at a return back by 2. Here I return back by 4. So this is the farthest value that I saved about this system, by about the x, the value of the input. This is the first thing. Before that I don't save it, I just use it in at that time, or save it for next or next one. Then this is the value 4. So how far, when I say how far, I say the last one in memory, or the far value of memory that I save it. It may be in the future, maybe in the past. Okay, so 4 time units. Okay, this one. Another example, the input time output of a semiconductor diode, he say that I of t, A0, A1, V of t, VT, VT, whatever it is. However, what you see here, it is an equation. Yes, it is an equation. But I have here V of t, V of t, V of t. So all of them is in the present, so I don't have any t minus 1, t minus 2, plus, so all of them is in the present. Then this system, I say that this system is memoryless. Okay. Third, the causality. uh, Causality is depending on causality, yes, not causality, causality, because it have a cause. If the output depends on the present or past value of input signal. So only the difference between memory it's saving something different, something different than the present about the my signal. But causality is having what is causing this signal. The causing of the signal is the present or the past. Yes, so the present or the past version of the signal is, if I have it in my hand, then this system is causal. If there is a version of the future signal, or the future version of the future value of this signal, of the out input signal, then this system is not causal. Okay, so this system here, x of n, x of minus 1, x of minus 2, so it is past present, then this system is causal. The signal, the different version of the signal, for example, if x of n plus 1, x of n, x of n minus 1, both of them are moving average, of course, because moving average maybe it's 4 over 4, maybe 6, just having 3 or 4 the following or success of the signal itself. So you take, for example, 1 2 3 of the signal and divide it by 3, not taking 1 2 4 or 1 2 6, for example. Okay, so the system is not causal because we have a future here, but it is a memory. Yes, because it have a past, present, and have a future here. There is a future and a past exist, but it is not it's non-causal. Okay, you should say that, because the checkup is just saying that a check for the following system, if they are memoryless, if they are causal or not, if they the linearity. So I give you some systems, yes, and I ask about one or two or three properties of that system. Okay. Now, let's say that there is another one called time variance. Time variance means that if that there is a time delay or advance in the input signal, it should result in the same shift in the output. So this system doesn't have any effect on delaying effect or advancing in time. So the system directly gives the effect of the system directly without any delay, without any shifting on time of the original signal. Okay. Example is the discrete time system described by the input output. Yes, this one, y of n equal r to the power n x of n, if it is time variant or not. Okay, it is a time variant, but what is the solution? The solution for time variant, you have to shift the input first, and then you have to shift the output, and then you will see if they are both or not, same or not, equal or not. Okay, let's see what's happening. Put each n, remove each n by n minus n0 in the input. I'm sorry for the writing, but it should be subscribed like the n is in and this small zero or small n zero, small zero under n. Okay, I think you understand me. Now, when in the input, where is the input? Only the input. I look to the input x of n. So w of n, a new version, equal to r to the power n x of n minus n0. Why I didn't put here? Because this is not the input. This is related to the output. So I just look at x. Where is x in my equation? I put inside it. I the subscribe from subtract from n and n0. Okay, then I will have this equation. Next step is putting each n by removing or replacing each n by n minus 1 or n minus n0. I think this is a problem here. N minus n0. I think replace is much accurate. Yes. Oh. Yes. Okay. So replace each n by n minus n0 in the input, which gives me this. Only this I replace here in x because x is the input, and then replace the next step is replace each n by n minus n0 in the output. Then the output here it affecting all the equations, so I replace each n I see, I replace it by n minus n0, n minus n0. Okay, now look at y of n or w of n or and y of n minus n0. What is the difference? Are they equal or not? No, they are equal in this part, but this part is different. So w of n not equal to y of n minus n0, so this is a time variant. So there is a delay in this system. This vary with time because it's have a equation or have a part of the equation that depend on the time. Okay, now let's go to the last one, linearity. Linearity means two conditions or two parts that give me something that I can say that this system is linear. That first one or the easy one, the second one here, the homogeneity. Homogeneity is like I multiply a value, a positive or a negative, a value, a constant number, or that's bounded. So a, b, c, whatever, this have a value 5, 4, 6, whatever, and multiplied by the I multiplied by the input, and then I should see it in the output. For example, if I multiply a by x of 1 of t, I should see that in the output the a is same there. It is still there. This is homogeneity. Superposition is the first one, which is meaning that if I give the system x1 of t, okay, then I should have y1 of t. Okay, this is easy. If I give the input the system x2 of t, another version or another input number 2, then I will have output number 2 y2 of t. Okay, then I have two inputs, I have two outputs. What about if I summation, I take the summation of x1 of t and x2 of t? What is the output? If the output is equal to y1 of t plus y2 of t, then this meaning that is superposition. This meaning that this condition is okay, and if homogeneity is okay, then these two conditions satisfy that this system is linear. If none one of them satisfied, then or either neither one of them is satisfied, for example the homogeneity is satisfied but superposition no, then linearity is this, I say this system is non-linear. Okay, let's see an example. The example say that the linear discrete time system y of n equal n multiplied by x of n. Check if it is linear or no or not. Okay, so first I should multiply by something. Yes, I should multiply by a. So I multiplied by a here. I know that there is different ways of checking out that what is the superposition and homogeneity, but this is the way in the book. I accept another ways. I will or I will. There is another way in the different books from book to book for solving the solutions the this kind of problems. It is okay. So x of n equal to the summation of a of 1 x of I. So ai is the homogeneity, this one. I multiplied both of them. So if I want to check both of them again at the same way, I multiplied a and multiplied a2 here. So if I see a here, the a here and a2 here again, then I checked homogeneity and superposition at the same time. That's what he put here. He takes the summation but he takes the summation for n, maybe 10 or 11. Okay, and he multiplied by a on the inputs, not the output. I didn't go to the output until now. So I take the summation of the input, I multiply all of them by a different value, a finite value of a. Then why I take the output signal, and let's see the output signals. I will remove this. I will take this, the output signal, the x of n, the new x of n, and I put it in the output. Okay, let's see. Now n, I can put it inside, yes, because n it is a value 1 2 3 4. So it can go inside or outside because it doesn't depend on the I. Yes, so if it is go inside, then n x o I of n, it is the same as y of n, as we see before. So it is y I of n. Yes, so what is a I y I of n? It is the value of all of y's multiplied by a. So I see I y1 or y2 multiplied by a1 a2, the same idea that I checked for the homogeneity. Yes, and also the summation doesn't affect the values. We will see that there is some systems that affecting. I can't put inside the a, I can't take it inside, or the a it's affecting, or I can't it's affecting by a different way. So let's see here, y I of n equal to n equal n multiplied by x I of n. So this system is a very simple system that say that this is linear. I checked both of the condition and is okay. Okay, So this is the end of the lecture. I will upload some examples, more examples. There is a lot of examples in the book, and thank you for listening.